Hello guys, welcome to this new video. So now I'm going to go through the paper 1B section of the specimen paper from the new 2025 syllabus. So here we will have two data analysis questions. The first one, we have a group of students investigating the motion of a conducting ball suspended from this long string. And we are told that there are two vertical metal plates that have an electric potential difference of V between them. The ball is allowed to touch one of these plates so that it becomes electrically charged and then is repelled from the plate. And for a given potential difference, this ball is basically bouncing back and forth with a constant period. In part A, we're told that the students vary V and measure the time t for the ball to move once from a plate to the other. So from here to here. And we're given this table of data. We're told V is provided by two identical power supplies connected in series, and the potential difference of each of the power supplies is known with an uncertainty of 0.01 kilovolts. We need to state the uncertainty in the potential difference of V. So basically what we need to imagine here is that this battery source over here is made up of two batteries. So we have two batteries connected in series, just like this. And then we have the rest of the circuit over here. And well, when we have two batteries in series here, their overall potential adds. So we have to add the potentials. Here that's not super important because we don't need to calculate any potentials. We just need to consider their absolute uncertainties. So let's say that this is some V1, this is some V2. So the overall V will be V1 plus V2. And when we add two variables like this, what we have to do with their uncertainty is add their absolute uncertainties. If we would be multiplying them, then what we would do is add their fractional uncertainties, where the fractional uncertainty is the absolute uncertainty divided by the actual value, like this. And then we would add this with delta V2 over V2. But here we're adding variables, so all we do is add their absolute uncertainties. So 0.1 plus 0.1 gives us 0.2 kilovolts. All right. And in part 2, we're told T is measured with an electronic stopwatch that measures to the nearest 0.1 seconds. We need to describe how an uncertainty in T of less than 0.1 seconds can be achieved using this stopwatch. So what we can do here is what the students did here was calculate the time T for the ball to move once from one plate to the other. So they basically calculated one period, started here and ended here. So here the relative uncertainty is going to be pretty large. The uncertainty will be very large compared to what we're measuring. What we can do is let the ball bounce multiple times and let the stopwatch running. So maybe we start the stopwatch over here, we let it bounce maybe 10 times, and then we stop the stopwatch. And then we divide this recorded time by 10, and then the uncertainty will be lower because we're measuring the average time basically. So what we could say is to measure time for many bounces. And what we will have to do is divide by the number of bounces we measured so that we calculate the time, so that we end up with the time needed for one bounce. So divide by the number of bounces. Alright, and now we have a graph showing the variation of T with V. We're given the uncertainty in V. We need to outline why it is unlikely that the relationship between T and V is linear. So in a question like this, what we need to say is that it is not possible to draw a straight line that passes through all the error bars. So not possible to draw an error bar. Not possible to draw a straight line that passes through all error bars. So this is basically word for word what we need to say for all kinds of these questions. These questions come up quite often. Another common one is whether two variables are directly proportional. For that, we need this condition I wrote over here, and the line has to pass through the origin. So those are two conditions for direct proportionality. Here I can obviously see that I can't really draw a straight line that passes through all error bars, some error bar is always going to be left out. So yeah, it's not quite possible here. And then we need to calculate the largest fractional uncertainty in t for this data. So as we said before, the fractional uncertainty is just the absolute uncertainty divided by the time. So in the actual time of the data point we're looking at. So this absolute uncertainty, if we look in the graph, is always going to be 0.1. It's always spanning these two rectangles for each of these data points on the y-axis. So the absolute uncertainty is always 0.1. We need to calculate the largest fractional uncertainty, which means that we need to input the smallest possible number here. So we need to see what is the smallest time. Well, we see this time, and then we quickly see what time it is corresponding to 0.5. And so we get that this is equal to 0.2 or 20%. So this is the largest fractional uncertainty. And then we now have the students who suggest this following relationship between t and v, where a is a constant, and then we have this t against 1 over v plotted. We need to determine a by using the line of best fit. So if I draw the line of best fit, it's going to look something like this, let's say. And then what I have to do here is measure, so what we see here is that this is of the form y equals mx plus b. So here b is equal to 0, so we have this model assumes no y-intercept, or like a y-intercept of 0, so direct proportionality. And as we can see here, y is the t, so the y variable is t, and the x variable is 1 over v, as we can see. So what that leaves us with is that the slope is equal to a. So from this we see that the slope is equal to a. So all I need to do here is calculate the slope of this line. So this obviously depends on how well I draw the line, how well it passes through all the error like closely to all the points. Usually what I want is the same number of points being above and below the line. So maybe something like this would be better. Yeah, approximately. And then what I need to do is calculate the slope. So preferably we can see two axis intercepts, for example this over here, and I'm looking for a point where it passes through two axis lines, two grid lines very cleanly, because those are always much easier to read off. It's a lot more practical. Maybe this one over here. Another thing to keep in mind is usually we want to select 2 points that are relatively far away, and of course we don't want to select any of these data points. We always have to calculate the slope of the line that we are drawing in the trend line. So this will have coordinates of 0.05 comma 0.2. This will have coordinates of 0.24 comma 1. So the slope is going to be equal to a. In this case is going to be, well, the slope is always delta y over delta x, change in y over change in x. So the change in y is 1 minus 0.2. Yes, and the change in x is 0.24 minus 0.05. So we have to divide this by 0.19. And well, if I do this, then I get 4.2 for a. Now the mark scheme says accept anything in between 3.8 and 4.2. So I probably drew this a little bit too steep. Indeed, I can see like 2 of these data points being under the line, maybe even 3. Here we only have really 1. I probably could have drawn a little bit less steep, and then it would have been better. But yeah, so anything between 3.8 and 4.2 is accepted here. Obviously, if you have a ruler, then you can more accurately determine where you want to draw the line. Here it's a little bit hard for me. And then in part 2, we need to state the units of a. So for the units of a, we just consider what we did. So a is change in y over change in x. So we just do the units of y divided by the units of x. So units of y was s. We divided by the units of x, which is 1 over kilovolts. So 1 over kilovolts. So this will just be seconds times kilovolts. Maybe it looks better if we write the kilo at the start, like this. And then in part 3, the theoretical relationships assumes that the ball is only affected by the gravitational force. We need to explain why the length of the string should be much greater than the distance between the plates. So I want to draw a diagram for this so that we can actually see what is happening here. So we need to see why the length of the string has to be much larger than the distance between the plates. So if we imagine here, we're going to have, let's just consider the forces that are acting here, right? So we have gravitational force, we have the electric force, and we also have tension in the string. Now, in this experiment, what we are investigating is the effect of the potential difference on the time period, right? This is what we're trying to investigate. We're changing the potential and we're measuring the change in the times, also what this model represented. So essentially what we want is really only the electric force should be affecting this experiment. We don't really want any other forces that shift the results of our experiment. And actually something that does this is the tension, because if we consider the tension here as two components, there's an x component and a y component. If we consider these x and y usual axes, and well, this dx component we don't really account for, right? Nowhere in the experiment did we account for this shift in the force. And so ideally what we want is that the dx should be very small. Should be very small so that it doesn't affect the experiment. And if we consider how we could do this, usually the common description of a pendulum like this is the angle that it makes with the vertical, because with this we can also calculate the component here of Tx in correspondence to the tension force. And well, what we see here is, well, firstly, we don't need to go too much into detail here, but this here is also going to be this angle phi, let's say. And so this tension force will be the sine of this phi. And so we can say that Tx is equal to T times sine phi, right? This is going to be magnitude of Tx. What we want is this angle to be very small. And the way we can do that is by making this very high up and keeping the plates still the same distance away. And this angle will become very, very small. So if that angle is very, very small, then if we consider the sine graph, right, if theta is very small, it will be very close to 0. Therefore, Tx will be close to 0 if phi is small. So this is the sine graph, and for very small values, it's approximately equal to phi, and we want this to be very small. And the way we can do this is by making this length much larger than the distance between the plates. So yeah, this is kind of the reasoning here. And then question 2, we have a group of students investigating the bending of a plastic ruler. We have some weight clamped on one of the ends, and we're measuring this distance that this ruler bends down. We have a constant length L, and the group obtains the following readings for one value of W. So the group divides into two subgroups. A and B analyze the data, and group A says that the mean value is 2.93 centimeters, whereas group B says 2.8 centimeters for the mean. We need to discuss the values that the groups have quoted. So firstly, group A, this is inappropriate because all of these readings are to two significant figures, and they have added an extra significant figure into their mean value. This cannot be. So too many sig figs in the value of the mean. It should only be 2. Well, B, they do state it's two significant figures, so that's not the issue here. And well, I'm going to be honest, noticing this, or at least what the mark scheme says, I probably would have never thought of this on my own. So what group B did was assume that 3.6 was an outlier. So if we would calculate the mean value of only these 5 data points, we get 2.8. I guess we can kind of see that because these two form an average of 2.8. We have 2.8 here, and again, these two form an average of 2.8. So a mean of 2.8. So I guess we can kind of see that 2.8 is the average of these 5 numbers. But yeah, so they considered 3.6 to be as an outlier. So 3.6 was an outlier according to them. Like this. Now we're given a variation of D with this weight we placed. We need to outline one experimental reason why the graph does not go through the origin. So we kind of have to imagine what's happening here. This basically means that if the graph doesn't go through the origin, even if we have a mass of 0 here, if we have no weight over here, there's still some small deflection here. And we kind of have to state why this might be. And well, one of the reasons is that the ruler has a weight of its own. So the ruler will bend under its own weight. It will bend down a little bit. Another reason we could state is a systematic error. So we could consider all the data points being shifted for some reason. And for example, in the measuring device we use to measure D, there could be some systematic error that it's constantly shifting our data points upwards here. And then we're given that the theory predicts that the deflection down is proportional to the weight to the power of x multiplied by the length of the ruler to the power of y divided by this two kind of constants, E and I, which are, well, E is a material property, I is a property of the cross section of our ruler. In IB we don't learn anything about this, but we also don't need to because we're provided the SI units for these, so that's all we need. But this is actually a theory that this is how we this is like an actual theory here. It is not something that just the IB came up with, obviously. So what we have to do here is just find the units of the x and y. I mean, not the units, but the powers x and y. The way we can do that is by considering the units on the left and on the right. So we can do some unit analysis here. So what we see is that D is the distance bending down. That will be in units of meters. We know L is also meters because that's the length of the ruler. We're given I is meter to the fourth, and we're given E is kilograms meter to the -1 s -2. Now weight is the weight we place. We know that weight is a force. Force is mass times acceleration. So the SI units of that would be the kilogram for mass and meters times second -2 for acceleration. And if we raise these two to the power of x and this to the power of y, the units on the right has to be equal to the units on the left. And that's how we can find x and y. So we are given that m is equal to kilogram meter second -2 m to the y, like this, and is divided by kilogram, and then let me combine meter to the fourth with meter to the -1 to make meter cubed and s -2. So what we need is that once we simplify all of this, it just becomes meters. So what we see is that the seconds have to cancel out. The only way that's going to happen is if x is equal to 1. So x must be equal to 1, otherwise the seconds won't cancel. So if x is equal to 1, I can rewrite this formula. So we have meters is equal to kilogram meters meter to the y. So let's just say y plus 1. And is divided by kilograms meter cubed, like this. And so what we see here is that, well, kilogram cancels out. And then we get that this is meter to the y -2, and we get that the exponents obviously have to be the same, so we want m to the first power here, so we get that y is equal to 1. I mean, no, I mean equal to 3, obviously. 3 minus 2 is going to be this one over here. So that's how we can calculate the deflection, and this deflection will be proportional to this value. All right, and then part D, kind of unrelated here. The ruler has a cross-sectional area of AB, where A is 28 plus minus 1 millimeters and B is 3 plus minus 0.05 millimeters. We just suggest an appropriate measuring instrument for determining B. And well, this kind of just is asking for our knowledge of measuring instruments. Common one is just the vernier caliper. This is probably the most well-known one that we also might have used already during IB experiments. Some more special ones or some slightly more accurate one is known as the micrometer, screw, gauge. These are generally more precise than vernier calipers. You can search what these are up. They basically have, it's a micrometer, and yeah, so these are, but the vernier caliper is obviously the most well-known one, I think, in the IB. And then in part 2, finally, for this paper, we need to calculate the percentage uncertainty in the value of A. So just like I mentioned at the very beginning of this paper, percentage uncertainty and fractional uncertainty are very closely related. They just have a factor of 100, obviously. And when we multiply variables, what we have to do is add their fractional uncertainties. So we can say that the fractional uncertainty in A is just going to be the fractional uncertainty in small a plus the fractional uncertainty in small b. So this will simply be 1 divided by 28 plus 0.05 divided by 3. If we do this, we get that this is equal to 0.05, and therefore the percentage uncertainty is 5%, and that is the end of this paper. So yeah, I hope I was able to help with some of these explanations. I recommend you know how to propagate uncertainties really well, especially when we plus or add or subtract values, or when we divide and multiply. So when we add or subtract, we add their absolute uncertainties. When we multiply or divide, we add their fractional uncertainties. Obviously, raising to some power is just multiplying, so there as well, we just add their fractional uncertainties. So that would be my kind of last note. And well, if you're writing your exam tomorrow, then I wish you best of luck.